Take my word for it.
Oh, come now.
You'd like him. Yes, you would. You'd get along beautifully together.
If you love listening to this show, please consider giving a rating and a review on Amazon Alexa or wherever you listen. We want to continue bringing you this amazing content, and part of our ability to do that means that we need a big audience. Now, it may not seem like much, but rating and reviewing the show will help more people find us, just like how you found this show. Simply on any podcast platform, search for a show, scroll down to the bottom, and push 5 stars. It's that easy. Thanks for supporting the show. Today, I'm joined by Dr. Alexander Shkolnik, co-founder and CEO of LiquidPiston, that develops advanced internal combustion engines through its patented thermodynamic cycle and engine technologies. Thanks for joining today.
Thank you. It's a pleasure to be here.
So you have a PhD from MIT CSAIL, and where you've worked on high dimensional motion planning for Lego robots. Can you tell us about some of the projects that you worked on there and how that kind of helped build some of the foundational aspects of what you're working on today?
Yeah, absolutely. So again, it's a pleasure to be here today and to talk to you about our company and kind of how I got here. But my background is primarily technical, degrees in computer science and math, also neuroscience, behavioral biology, and then did my PhD at MIT. So you might ask what's the string that knits all that together? How are robots and neurons and engines, how do they all relate? And for me, I enjoy math, and once you present something in a mathematical framework, you can start to play with it, and that's what I enjoy doing. I like modeling things and then seeing where those models can take you. So the skills that I developed at MIT in walking robotics, it sounds very far away from an engine, but I was able to work with my father, who was I guess I'll back up a little bit. When I first got to MIT, my father's a physicist, and he was working on this new engine idea that he had. And so I just started by helping him, right? I was just modeling a little bit for him, doing some tool development, a little bit of optimization. And he kind of approached the problem of the combustion engine from a pure physics perspective, right? He was looking at the car that you might drive, which only converts about 15, maybe 20% of the energy in the fuel into useful mechanical work. And so as a physicist, that always bothered him. Why are we leaving 80% of the energy in the fuel as something that we're not making into something useful for us, right? We're just wasting it as heat. And the physicist in him said that we can do better than that. And so, we just kind of combined physics and modeling and drove the idea further and further until achieving where we are today.
Yeah, I think that's a really great setup to talk about what LiquidPiston does. So if you could explain a little bit and how you guys are revolutionizing the traditional pistonless rotary engine.
Yeah, absolutely. So as a company, we developed very efficient, very compact rotary engines. And, we converged on the idea of a rotary, but it's based on a new type of thermodynamic cycle. We call it the high efficiency hybrid cycle. The reason we call it a hybrid cycle is because we are essentially cherry picking features of a lot of other cycles that we would like to have in our cycle. So it's a new cycle that's optimized for fuel efficiency. And the way we embody that is with a rotary engine. So it's a very simple device. This is one of our prototypes, just as an example. It's about 5 pounds, produces 5 horsepower. And it's got 2 moving parts inside of it. So a lot of your viewers may be familiar with the old Wankel rotary engine. Some of you might have had the RX-8 or the RX-7 car from Mazda that was in production for a while. The rotary engine has almost a cult following amongst engineers. It's known and favored because it's very simple. It's a very responsive engine, very low vibration, very high speed operation with it. But it always had some problems, right? It struggled with things like sealing, so it had a lot of blow-by, with cooling and emissions, efficiency, durability. It chugged oil. So really everything that the consumer, the average consumer, cared about, that engine kind of struggled with. So it never really fully took off commercially. So we have a new take on that on the rotary engine. We essentially turned it inside out. And the most fundamental difference is this new thermodynamic cycle, which can be 30 to 50% more fuel efficient. But also we solved the inherent challenges of the rotary with the sealing and the lubrication and things like that.
Yeah, so just to kind of review a little bit, is that, when we think about a traditional rotary engine, like the model we talked about, the traditional Wankel engine, it has a triangular rotor.
That's right.
And the three operating chambers are separated by seals installed on the three apexes of the motor.
Yep.
The issue is when the seals move in and move out during each of the rotation, it's subject to a high degree of stress and wear, which then limits the longevity of the engines, and that's exactly what you're talking about. And can you go into a little bit around how you guys have addressed that through the oval rotor that moves within a triangular housing?
Yeah. So the sealing is the Achilles heel of the rotary. Because they have corners, they have the apexes that you were talking about, but also a face seal that seals along the axial surface of the rotor. The real problem comes in the corners, where you have to allow for things to get hot in the engine, so things thermally expand. And in those corners, there's pathways for air to leak. And when you have leakage in your engine blow-by, you get poor performance and poor fuel economy. But what we did is we essentially turned the old rotary inside out. So instead of having a triangular rotor that operates within a oval-shaped housing, we have a oval-shaped rotor that operates within a tri-lobed housing. So take everything you might know about the Wankel engine and literally turn it inside out. So the Wankel has a long, skinny combustion chamber that's moving. And that's probably the worst thing you could do for an engine in terms of combustion. You get very poor combustion characteristics there because the combustion develops like a ball, and when it hits the wall, it extinguishes. So imagine trying to grow a ball within a narrow corridor, and quickly you find out that you can't do that, right? The flame hits the wall, it burns out, and you end up with very poor combustion. In our case, the chambers are located in the housing. They're stationary. They can be thermally insulated, and they can really be shaped to promote optimal combustion. And then, as you point out, in our case, the seals here are stationary at the three apex points, but now they're inside the housing. They don't move at all. And we have a much more natural interface with the face seal. So we remove those the buttons that have blow-by in the Wankel. So we have about 5 times less blow-by than a traditional rotary. And perhaps most importantly, with the stationary seals, it means we can lubricate them directly. So we can supply tiny amounts of oil right to the surface that needs it most. In a Wankel engine, you have to literally dump oil into your air, and a small fraction of the oil gets to the seal. In our case, we can deliver the oil that those seals need right to them because they're stationary, because they're not moving. So that means we don't have to burn the oil, which solves really the biggest challenge of the rotary, which is durability and emissions because of how they lubricate their seals.
Mm-hmm. Yeah, I think as I'm listening, what makes the liquid piston model so interesting is the simplicity and the elegance. Now, of course, it's not simple, but coming back to the narrative around modeling through your father's physics and your modeling, you really kind of looked at the problem in a fundamentally different way. I think many times when it comes to invention, we just kind of take what the predecessors have done and say, how can we incrementally improve it? Here, really ask the question of why. And I love just the thought process and the elegance of the product that you guys have produced and then the modeling that's gone into it for efficiency. Just to give some reference, I believe a typical piston diesel engine uses some 15:1 or 24:1 ratios. You guys are projected to, I guess, have compression ratio of about 26:1. Is that right?
We've operated the engine up to a 26:1 compression ratio, but the key thing here is that no other Wankel rotary engine has operated on a diesel cycle. So the reason that diesel engines are more efficient than gasoline engines is because they can achieve the high compression ratio. That's why a diesel car gets better MPGs than a gasoline car. So we are able to capture that with our rotary design. Because we can displace all of the gas into this stationary chamber, we can drive up the compression ratios, and we design the engine to operate like a traditional diesel. The other thing is that we can inject fuel directly into the combustion chamber because the chamber is stationary, unlike the old rotary that had the moving chamber. So those are kind of the necessary ingredients to operate on diesel. Now, if somebody asked you what's more efficient, the diesel cycle or the auto cycle, it's actually a trick question, right? The diesel is, in practice, it's more efficient because of the compression ratio. But the fact is that the combustion process of the auto cycle is actually better. The combustion process in an auto cycle is modeled as constant volume, which means you achieve all of your combustion while the volume is at its smallest point at the maximum compression of the engine. And that's what we're working to achieve as well. So in addition to a high compression ratio like a diesel, the problem with a diesel, they don't inject fuel until after you compress or right when you are approaching the compression point. So it takes time for that fuel to be injected, for it to mix and burn to completion. While you're doing that, your piston is expanding, and that's actually causing your pressures to drop. So it's if you look at the thermodynamic diagram, the PV diagram, a diesel cycle chops off the whole top of the curve, and they're leaving efficiency on the table. So what we're doing is we're combining these two cycles together, high compression, and then we keep the volume constant, and we give the engine more time to burn more completely. You reach higher pressures in the chamber, and then you expand. And when you do that, you fully expand. So those are kind of the key ingredients to our cycle advancements.
So I think you're referring to the Otto cycle and the Atkinson cycle too.
Exactly.
And again, I wish we had more time to go into it, but our time allotment doesn't quite allow for that.
Of course.
Let's talk a little bit about applications. So
yes.
How does it potentially change the game for EV vehicles or drones or any type of smaller vehicles or even flying vehicles for that matter, that will become more pervasive?
Yeah. So, I mean, we're a startup company. We're looking for the right kind of application fit to take this into the market. Ultimately, our technology can be scaled into anywhere that engines are used today. It's a $400 billion market out there for engines. And also we're competitive with small turbines, so turbines below 1,000 horsepower. But the question for us is really, where do we start, right? And for us, it's defense and aerospace. These markets, they need solutions that operate on heavy fuel, jet fuel specifically. And so that means they're limited right now to either diesel engines or small turbines. So that's where we're really focused, because they're very sensitive to size, weight, and fuel efficiency. And these are all the areas where we can help. Our engines are about 10 times smaller and lighter than a traditional diesel engine. It puts them into the power to weight class of a turbine. When you look at a turbine, a turbine is an incredibly power dense machine. The small turbines are very inefficient, but in addition to that, they also have all these ancillary systems around them. And so when you look at the overall system, we can be competitive with a turbine, but with fuel efficiency better than a diesel. And for these types of applications, that means, double the range of what they have available today. So that's a really big deal.
It's a huge deal, and I think we can't underestimate some of the technical achievements that you're referring to, and to be able to be in the class of turbines, but at more competing like at the diesel level, And then the cost and the efficiency, and of course the maintenance. That's the other piece. It is
Right.
It's not just the initial capital investment cost, but the maintenance of it becomes problematic, especially things that have a higher reuse, whether it's satellites or drones that have multiple missions and so forth. So the overall total cost of ownership becomes highly important as well. I wish we had more time. One last question for you is, what's next for LiquidPiston?
Well, so we're at this kind of inflection point right now. The technology has just been proven in the sense that we've inserted it into a number of application demonstrators. So, we've put the engine into a small vehicle. You can actually come to our shop and drive around in a go-kart powered by one of our engines. Recently for the Army, we demonstrated a parallel electric hybrid UAV. And the cool thing there is we can show on jet fuel, we can shut the engine off, and we can switch between the engine and electrical cruise modes of flight, and actually restart the engine, mid-air on jet fuel. So that's a capability that's never been fielded before.
Very interesting.
And in the last year, we've started working with a number of industrial partners. So we've signed 4 contracts with partners. And so this really represents the maturing of the technology. And what's next for us is to kind of cross the hurdle into commercial avenues, right? We're looking to demonstrate the durability of the platforms. We're looking to industrialize and productize the engine and get the engine into a first application, a real application, and then let the dominoes fall from there. So I would encourage your listeners to check out our website, liquidpiston.com, and there's actually opportunities for folks to get involved directly with us right now.
So today I've been joined by Dr. Alexander Shkolnik, who is the CEO of LiquidPiston. Thanks for joining today.
Thank you very much.
If you've enjoyed this episode, take a moment to rate our show on any podcast platform that you listen to. Scroll down to the bottom and push 5 stars. It's that easy. And as always, thanks for listening.